Let's continue with propositional logic in this first section. So we're working with propositions that could be called P, Q, R, any letter. And they take one of two values. They're either true T or false F. Okay, and then we looked at last time the different operations. So we have negation, and we have the conjunction and, disjunction or, and we have the exclusive or, and implication. Alright, so these let us combine propositions in different ways to get new propositions. So example 1, so here we're combining the propositions P, Q, just P and Q. So this is called a compound proposition. This is kind of a combination. And here we're also told that P is true and Q is false. Okay, so can we work this out? So the answer will be a truth value. This whole thing has to be either true or false. Yeah, the first thing to notice is these negations, they should be done first, like an order of operations. So we'll take care of this negation first, but that's easy. So if P is true, then its negation is false. So this turns into an F. And then we're just substituting, so we get F or, and then in parentheses, so do these two first or next, P and Q, so that's true and false. So we remember how that and worked. So the only time and gives true is when these two are both true. Otherwise it's false. So this piece is false. And then the last step is we have false or false, and that's also false. So for or, you need one of these to be true, or both. That makes it true. But since they're both false here, false or false is false. Alright, so the whole thing worked out to be false. Alright, so it's very similar to evaluating algebraic expressions by putting in numbers. Just the difference here is we have different kinds of operations, and the variables are either true or false. We looked at the implication operation last time. So this conditional statement, P implies Q. Again, we saw different ways to say it. You could say if P then Q, or Q if P. So for this basic implication, there are three related statements. Okay, so for any implication, the contrapositive is the new proposition, not Q implies not P. You also have the converse, so that's Q implies P. Okay, so that's just switching the two letters. And also the inverse, that's the last combination, not P implies not Q. Alright, so yeah, it's getting a bit confusing. But the main one we're interested in is this contrapositive. Not Q implies not P. Alright, so we can compare the truth tables, the contrapositive and the original. Okay, so if you remember from last time, this is the implication truth table. The implication, it's always true except in this one case where P is true and Q is false. Okay, so you can't have something true implying something that's false. That's the only time the implication doesn't work. Well, let's work out the contrapositive version. Okay, so let's say we have TT, P is true and Q is true. Can we work this out? Well, not Q, that'll be false, implying false. So false implying false, that's true. So we get a T. If P is true and Q is false, then we're getting a T here and an F here. True implies false, we know that's false. Okay, so we get an F. And do these the same way, you'll get true and true. So we see, yeah, we're getting the same, it's really the same truth table. It has the same T's and F's coming out. Okay, so if two compound propositions have the same truth table, then we say that they're equivalent. Alright, so this is working this out. This is telling us that an implication is really equivalent to, logically the same as, its contrapositive. Okay, I think I'm saying that here. Yeah, so the contrapositive, it's just an equivalent way of saying the original implication. But the converse and the inverse, those are not the same. So if you work out the truth table for Q implies P, you'll see you get a different T's and F's. And the same thing for the inverse. Yeah, in fact, the converse and the inverse are equivalent to each other, but not to the original or the contrapositive. Alright, so let's see an example. Yeah, here we are. So in the book on page 9, so we have this conditional statement: the home team wins whenever it is raining. Okay, so why is this a conditional statement? What's the implication? Yeah, whenever, that word, it's the same as if. So the home team wins if it is raining. Or you could say, if it is raining, the home team wins. So P here is it is raining, Q is the home team wins. Yeah, here it is, written out like that. Okay, so what's the contrapositive? All right, so the contrapositive is not Q implies not P. So here's the Q. So if the home team does not win, then it is not raining. So that's the contrapositive. Not Q implies not P. Okay, the converse, that's just switching. So Q implies P is if the home team wins, then it is raining. And the inverse is the not version. If it is not raining, then the home team does not win. All right, so yeah, if you think about it, these last two, these are different, have a different meaning to the original. So again, the original says, yeah, if it is raining, then the home team wins. That's the same as saying if the home team does not win, then it is not raining. So logically equivalent. Okay, so our last operation is the biconditional statement. So what's that definition? So P and Q propositions. Then here we have a P and a Q with an arrow going both ways. And you read it P if and only if Q. And this new proposition is true when P and Q have the same truth value, and it's false otherwise. So if P and Q are both true or both false, then the biconditional is true. But if one is true and one is false, then it's false. And yeah, we can understand this if and only if. So yeah, remember P only if Q. So that's the same as just the implication P implies Q. P if Q, that's the implication, if Q then P, that's Q implies P. Okay, so you can see we have P if and only if Q means arrows going in both directions. It's equivalent to P implies Q and Q implies P. So we're really nailing down that the P and Q have to have the same truth value for the biconditional to be true. Okay, so TT gives a T, FF gives a T, but if the P and Q have different truth values, then it's false. Okay, yeah, so we'll use this a lot. So if and only if, so P if and only if Q, that whole thing is true if and only if they have the same truth value. Yeah, it's also, you can say it, P is necessary and sufficient for Q. So implications going in both directions. An example of that, so example 2, suppose P says it is raining, and Q says the streets are wet, if Q is true and P, if and only if Q is true, what can we say about P? Well, if this biconditional is true, that means they have to have the same truth values. So if Q is true, then P has to be true. So if the streets are wet, then yeah, it is raining. Okay, I think that was our last operation. But we can use all our operations, so this biconditional along with these guys to make new propositions. So making new combinations, that's called a compound proposition. And if you want to understand a compound proposition, then a good way is to write down its truth table, which just looks at every possible truth value for the propositions involved, and so you can see how the compound proposition works. Example 3, this is a simple example just with a P. Give the truth table for P and not P. Alright, so yeah, P is either true or false, so our table, we'll just have 2 rows. The first row, P is true. The second row, P is false. Okay, we're working out this whole thing, but we can do it in stages. So first we'll write down P's truth value. And then we can write down the truth value of this piece. So not P, that just switches. And then apply the AND operation. So we have true and false. Well, that's false. And then we have false and true, that's also false. So we need 2 trues to get a true from the AND operation. Alright, so we see that this combination, it's always false. So it doesn't matter what P is, this always returns a false value. So we'll look at things like this in section 1.3 in more detail. Okay, but you get the idea. So just making a truth table just to look at every possible combination. Yeah, if we had a P and a Q, then we need 4 rows. And if we had a P, a Q, and an R, we'd need 8 rows to get every combination. So for every extra letter, it multiplies by 2. So example 4, yeah, we have a P, Q, and an R. So 8 rows for the truth table. And yeah, so it's important to kind of do it systematically. So this is a good way to do it. So so start off with true, true, true. Now the R's are going to alternate true, false, true, false. Then the Q's are going to change every 2 rows. And the P's every 4 rows. Okay, so starting with trues, here every row it switches, here every 2 rows, here every 4 rows. Alright, so we get all 8 possible combinations of P, Q, and R. Okay, so then we'll work out this piece first. So P implies Q, so that's worked out in this 4th column. Okay, so remember, yeah, P implies Q. That's always true except for true implies false. So yeah, so just these two give false. The rest of the time it's true. Q if and only if R. So we're looking for the same truth value. That'll give us a T. Okay, so these are the same. These are the same, and same. So just these 4 give us T's. And then the last step, this AND in the middle. Alright, so we're looking for, so for the AND to be true, we need 2 trues. Everything else is false. So yeah, when do we get 2 T's? So yeah, here, and here. Alright, so that everything else is an F. Alright, so it's a big table if you have 3 propositions, but this is the answer we're looking for. So you can, for any combination of P, Q, and R, you can see what the answer is going to be. And one in the book. Oh yeah, here's a compound proposition. Yeah, it just has P and Q. So just 4 rows. And again, you can work out each piece and give it a column. So here's not Q, switching the Q truth values. Then, oops. Then do this OR here. Then this piece, P and Q. And then finally the last combination we want, with the implication. Alright, so this whole compound gives true if P and Q are both true, or P is false and Q is true. Otherwise it gives false. Alright, so for any compound proposition, you can work out its truth table like this. And the last topic in this section, bit operations. Alright, so yeah, we should definitely talk about bits. So computers work with 1s and 0s. And the 1, yeah, that always represents true. 0 represents false. So we can, instead of trues and false, trues being true and being false, we can think of ones and zeros. So we could rewrite all our tables with zeros and ones. So here's the bit version of OR here. Okay, so remember 0 means false, 1 means true. Okay, so 1 or 1, that's the same as saying true or true, that's true. And so OR is true in every case except if you have 2 falses or 2 zeros. Here's the bit version of AND. So it's 0 unless you have 2 ones here. And here's the exclusive OR. So that's looking for 2 different valued bits. So if you have a 0 and a 1, or a 1 and a 0, it gives 1. If the bits are the same, it gives 0. Alright, so we're just replacing T's by 1s and F's by 0s. And I guess the names here. So OR, that's the OR column. Here's the AND column. And exclusive OR, that's written XOR. Alright, so these bits, they're means something that's either 0 or 1. It comes from binary digit. The B from binary and the IT from digit, so that's bit. And a bit string, that's just a sequence of bits. And so here's a bit string, so just zeros and ones of length 12 here. Okay, so 12 bits, but they could be any length. Alright, so internally computers are working with bit strings. And a common way to combine 2 bit strings, they need to have the same length, is to use, say, the AND operation. Okay, so bitwise AND means just compare each corresponding bit in the string and apply the operation. For example here, taking these 2 bit strings of length 3. So if we apply bitwise AND to these 2, so here's the first one on top, the second one on the bottom. We're just comparing the first 2 bits. Okay, so for AND, a 1 and a 0 gives a 0. AND is looking for 2 ones to give a 1. This if this is AND, then this 2 zeros, that's no good. That should be a 0 here. So the bits have to be true. Both true. Yeah, so this is the correct answer, so 0, 1, 0. And the same thing for, you can use bitwise or bitwise XOR, exclusive OR. So example 5, let's see if I got this one right. So A is this bit string, length 6. Here is B. First find the bitwise exclusive OR of A and B. And then the second part, find the bitwise exclusive OR of the answer from the first part with B again. Yeah, so good to write one string over the other. So for exclusive OR, we're looking for the bits to be different. That'll give us a 1. If they're the same, we get a 0. Okay, different, 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 same, so 0 here. So this is the answer for the first part. And then put that answer here and apply B bitwise exclusive OR that answer with B. Again, we're looking for different bits, so we get a 1 here, a 1 here, and a 1 here. Alright, so that's the answer for part B. And yeah, so we see we're back to A again. Yeah, if you exclusive OR the same string twice, you get back to the original. So this bitwise exclusive OR, yeah, you don't lose any information. You can get back to the original string if you apply it twice. Alright, so that's examples of these bitwise operations using our OR and an exclusive OR. Alright, I think that's it for this section.